All right, so let's see if we can clear up if there was any confusion on looking up some of these values. So this is where we ended up with our example on continuously braced beam design. And if you recall, the first thing to keep in mind is that after all of your analysis, you should end up with two values. You should end up with your required moment value and your required moment of inertia. Now, we also did the shear analysis while we were at it. But it shouldn't really affect the design. Now in step 3, what we're doing is the first thing that we're doing is we're selecting a section based off of moment. Now, since for a continuously braced beam, the capacity is MP, or the phi MP, the factored moment capacity, what I'm doing is I'm selecting based off of this column, the plastic moment. So I'm going down here, going down this column, okay, and I'm trying to find the lightest shape that has a phi MP greater than or equal to 789.7 foot kips. Okay, now what a lot of people did is they said, okay, 789.7, let's go with this. Okay, let's go with the 18 by 97. And the 18 by 97, sure, the 18 by 97 has enough capacity, but it weighs 97 pounds per foot. Remember, if you have a W18 by 97, let's remember what those two values are. The 18 is the depth, this is the weight, and this is where the money comes from. If I'm buying steel, I'm going to be buying steel per pound, right? So I want to spend the least amount possible, okay? So I'm going to go off of that second number. Now, and I think, one of the other answers we might have gotten was this one, and I think you might have been confusing the I don't remember who said that, but it might have been the depth versus the weight. That second, or that middle section, is the shallow one within that group, but it's also the heaviest, right? The answer that we want, however, is this one, because within that group, that is the lightest. There aren't any architectural limits on the problem, so there is that. So we're going off of the lightest. So we say try a W24 by 84. Now, we say try a W24 by 84 because we also have to look at the moment of inertia. See, for a W24 by 84, the moment of inertia is 2370, okay? So IX is 2370, but IX required was something like 3041, okay? Something like that, okay? That's a problem, okay? Here's what that means. Let's make sure we understand the meaning behind this selection. For the W24 by 84, it has enough strength, okay? The phi MP is 840, so to be clear, phi MP is 840. It does have enough strength, but it doesn't have enough flexural stiffness. It will deflect too much. Remember, there is a deflection limit of L over 600. If I pick the W24 by 84, it's not going to work. Another reason why we say it's a trial section is because in order to come up with those moments, we assumed the beam weighed 50 pounds per foot. This beam is heavier than that, so we're going to have to update our moments and shears accordingly. So this section is not going to work. The W24 by 84 is inadequate. Okay. So now what I'm going to do is I'm going to move to step 4. And I'm going to select a section based off the moment of inertia, because I can already tell for this problem that strength isn't going to govern the design. It's going to be the deflection limit. So I'm going to select based off of IX. Now, we had a moment of inertia requirement of 3041.4 inches to the fourth. So again, if I go down to this table, I could pick, this section, this W18 by 58. But again, it is heavier than this lighter shape here, the W30 by 90. The section is deeper, so you don't need as much steel, right? That's sort of the idea. So now we're going to try a W30 by 90. Now, before I start step 5 where I start grunting out the math and the computations, I might as well check the W30 by 90 to see if it's got enough flexural capacity as well. So I go back to table 3-2. Let me get my mouse here. Where'd my, there we go. Go to table 3-2. Here's table 3-2. Look at the W30 by 90. Does it have enough flexural capacity? Probably. And I say probably because, again, this section is heavier than the assumed self-weight. So we're going to have to update all of that. So the flexural capacity is 1060. The moment of inertia is 3610. This is a worthy section to do your assessment on. So let's try a W30 by 90. Okay. And so now we can get into step 5. All right. So step 5 is not hard, just maybe a little bit time consuming. So step 5, analyze the W30 by 90. Okay. And so all we're going to do is chug out a lot of the calcs that we had done before. So first off, let's do our dead loads. Let's update our dead loads all over again. So our let's recognize that we have a dead load of 1.2 kips per foot. Now, remember we had that self-weight, and that self-weight we had assumed to be 50 pounds per foot. It's now not 50 pounds per foot, it's 90 pounds per foot, or 0.09 kips per foot. So that beam is now heavier than what we assumed, so we're going to update our dead load shears and update our dead load moments. So from this, we're going to do VD and MD all over again. So this is WD plus W naught L over 2, which is 1.29 kips per foot, 35 feet over 2. So 22.575. And then MD is WD plus W naught L squared over 8, which is so that's 197.53 foot kips. So if you look, you can see these values are slightly higher than what we got before. If I scroll up here, I know it seemed, we did a lot of calcs there. This is what we got before, because we had a 50-pound self-weight, and we got 21.8 and 191.4. Now we've got 22.5 and 197.5. It's because the beam is heavier. It's heavier than the assumed weight. So you kind of need to go through and reassess that. Now that's the dead loads. For the live loads, we really don't need to update anything from what we got before. See, before, if you scroll up here, before, this was the case we were looking at. Remember, don't do that. Don't turn it into a distributed load. We got a VL of 20 kips and an ML of 350. Well, it's still a 35-foot beam with a 40 kip loaded midspan. That didn't change, because the live load was independent of what beam we picked. So I can still use the VL of 20 and the ML of 350. There's no problem using that all over again. So we'll say VL is 20 and ML is 350. Now what we've got to do is compute a new VU. And so 1.2 times this plus 1.6 times 20 is 59.09 kips, and MU is 1.2 moment dead plus 1.6 times. We'll call it 0.0 foot kips. Again, just because the beam got a little heavier. You know, the beam got a little heavier, so the shears increased just a little bit, moments increased just a little bit. Not a lot. I mean, if you look up here, we had a moment of 789.7, and now it's 797. So it upped a little bit. Not a lot, but you wouldn't know that unless you go through and do the calcs. So you kind of need to do that whenever the load, whenever the bending moment, whenever the self-weight increases. Now, if we had assumed something like a self-weight of 100 pounds per foot and we ended up picking a W30 by 90, I wouldn't worry about this because now the beam is lighter than what we assumed. If it can hold up 100 pounds per foot, it can certainly hold up 90. So if the assumption's the other way around, probably don't need to worry about this. But I still think it's not a bad idea just to go through the exercise. Okay, so here's VU and MU. And if we go back up here to the W30 by 90, I'm going to copy this just because I'm, want to make sure I've got this consistently. So we have, for example, VU is 59.09 kips and phi VN is right here. It's the W30 by 90, and we're looking at that. So that's 374 kips. So we know that our section is good. What about MU? MU is 797.0 foot kips. And phi MPX is 1060. We know we're good there. So we meet shear requirements. We meet moment requirements. Again, we probably don't need to do the math for the deflection requirements since there's not really any iteration. But just because this is your first time doing this, and just to make sure that you're comfortable with the selection, we might as well do the deflection calculation just to make sure. Now, if you remember for deflections, here I'll just do this right here. For deflections, we had that our maximum was L over 600, I believe it was. And L over 600, let me make sure I'm correct on that. Yeah, so L over 600. And so for L over 600, that ended up being, I believe it was 0.7 inches. Yeah, 35 times 12 over 600, right? So maybe I'll repeat that just to make sure everybody's clear on that. 35 feet over 600 times 12 inches per foot. Yep, so that's 0.7 inches. And then our live load deflection, actually, hold on, I'm naming this backwards. I'm going to call this limit. So that's the deflection limit. The maximum deflection that we're actually getting on the beam, let's use the consistent notation, is PL cubed over 48 EI. And so now we can just chug this out. We have everything that we need. So this was 40 kips. This is 35 feet cubed times, don't forget our conversion factor here up top of 1728. Over 48, 29,000 KSI. And now we're using, what moment of inertia are we using? This also might be something to clarify. We're analyzing the W30 by 90, so we're going to use the moment of inertia of the W30 by 90, which is 3610. And so we chug this out. So let's see. I'm getting 0.59 inches. So there we go. So if we want to summarize, summary. So for moment, So we have MU is 797. That's how much we're putting on it. PMN is 1060. That's how much it can withstand. We're good there. VU is 59.1 versus 374. We're good there. And then our deflection, our maximum deflection was 0.59. And then our limit was 0.7. So what do we got? We've got enough moment capacity, enough shear capacity, and its deflection is less than the limit. We're good. And if you want, this is not necessary, but if you would like, we can sort of check and see what was going to govern. So if I put some performance ratios out here, this is 0.752. I'm just taking the load over the resistance. This one over here, so 59.1 divided by 374 is 0.158. And this one is 0.843. So, what do we find here? So if I look at these, so again, shear, way more shear capacity than needed, not a problem. We met our moment and our deflection requirements, but also if you look at the performance ratios, you see that the performance ratio for deflection is higher. And that makes sense because of our process. Remember, we picked a section based off of the flexural capacity and it didn't work. And so then we had to go back and look at the deflections and find that it did. So, the math in the end also clarified our process. So hopefully that clarified some stuff up from the example today. And whatnot. If anybody has any questions, make sure that you just pop your mic off or pop your mic on and ask away. Hopefully this clarifies everything, and we will see you all on Friday.